So this short in this short video, we'll go over the first bit, which is of the course related to MOSFET DC operation. So the idea here is to give you an overview of MOSFET DC operation rather than going into the device physics, which you would be learning in other courses, either in your bachelor's or in your master's. So then when we look at MOSFET, we have already established that the planar MOSFET, which is typically what you would be using to design your circuits in this course. Planar means that it's a planar technology. That means the silicon wafer is like a plane, and whatever is deposited is on top of that, right? Which is what we talked about last time, that there is a gate contact, source contact, drain contact, and two pockets which are made for source and drain, specifically in your MOSFET. So then it happened to have these four terminals where the terminal which is coming from in between, or which is controlling the channel, which is what we are calling as a gate. Then there is a terminal which is which we know as where, or let's say if we are talking about N FET, so N channel FET, right? Um, N channel means that current is dominated by, or it is due to electrons, right? That is what I mean. So now to have the electrons here, we would know as from, if you go into the basic physics, you would know that you would need to apply certain positive gate voltage, so that because it's this portion which we are seeing here, there's a metal, right, which is our gate metal. Then there is something which is the oxide in between. This is your channel, or which we are, or the semiconductor, right, where we form a channel. So this is your semiconductor. So that is why, if you see, this is called MOSFET, because it's a MOS kind of combination. And this is the heart of your MOSFET, which we know of, right? So what we do is, what we want to do, because semiconductor itself is not conducting, what we have to do is we have to apply certain voltage, right? So when we apply certain voltage here at this gate terminal, which gives us, or which gives us the charge in the semiconductor. So this charge could be due to electrons, or this could be for p channel FET. It would be, which we know as the current is due to volts, right? So now it is, now if one understands that this is basically how we are generating charge in the MOSFET is through a capacitive action, then you know that if you apply a positive charge on the capacitor, one plate, you will have negative charge. So that is typically your electrons. And if I want a positive charge on the other plate, which is my channel plates, because this is your oxide, right? Then you have to apply negative charge here. So that is the basic concept, how we see that the VG which we need to apply for NFET, right, is positive, and the VG which we have to apply for PFET would be negative, right? So that is the part which we have seen from the point of view of the gate terminal. So the role of the gate terminal is basically to bring electrons or holes into channel. And where is the channel? It is underneath the oxide. So that is the part which the your gate does. So that is the MOS action. And now what is the FE which is called field effect transistor, right? So FET is your field effect. Now we have done the charge. Now how do we get the current from the charge? So that means the charge is not going to flow in the direction of the metal or the towards the gate, because there is an oxide stopping it, right? So that is like a big barrier because it's an insulating material. So then the charge would go from in this direction, right? So that is what you would see in a MOSFET. If you have, so this is the part we have already made, where there's a metal and this, right? So this is your gate. Now, and we, by applying certain positive or negative charge, gate voltage, we have brought in a negative or positive charge. Let's say if it is a NFET, it's a negative charge. Then what we do is that after this charge, once it has come into the channel, now we have to basically make it flow, right? So that is what would be meaning of the current which we will get out of these transistor. Because in the end, what is the output variable which we want is the current. When we apply certain voltage and there is a current coming out. So now to do that, we need to apply certain field, right? Because the charge would move if we know. So electric field, which we know as, right? So this charge would move as the, or the force on the charge would be applied by electrostatically QE. E means the electric field. And how do we generate this electric field? Now, if we want this charge to move in which direction, let's say if we want this charge to move from left to right. So if we want this to left to right, which direction should be your electric field? Because this is a negative charge, right? So here, if you want this charge to move from left to right, that means your electric field should be in this direction. If this is in this direction, that means force on the charge would be in this direction, right? Because there is a negative charge on the electron. So that is why if you want your electric field to be this direction, that means you have to apply positive voltage in this volt, right? And this on negative. And that is what we will call this as, this is your source terminal, because it is your charge starting your journey from the source terminal and it is going towards the drain terminal, right? So that is the, by definition, what we would call that, from where it starts and where it leads to, right? So this is the case which you will see that what is VDS doing, what is the role of VDS is to make the charge flow, right? Is to make the charge in the channel flow. So that is the effectively what your VDS does. Now, so that means now we can see that once we change the VDS, is there a change in the way you current it, or it changes just linearly? So that is the kind of thing one can investigate when they change the VDS. But what we understand from this DC operation, that the gate is controlling or bringing the charge in the channel, right? Which is kind of that if the FET is conducting or not conducting. So conducting means that if there is no charge in the channel, it would not conduct. So that means if you have not applied the gate potential, sufficient gate potential, that there is a charge in the channel, then it would not conduct even if you keep applying your VDS, right? Because there is no charge on which you can apply electric field. Similarly, if there is sufficient VGS, then you will see that there is a charge conducting. Now for a PFET, just to see that which, this is the metal, right? And we have applied negative on the metal, right? Negative, and so that's why you are getting positive charge here. And now if you want your positive charge to flow, so where it is originating from, let's say if we say from source to drain, so this is your source, right? If we are saying, and we want it to go towards this side, that means your electric field has to be the same, because force on the hole which we applied on, which is QE. So that means your source would be positive in this case and your drain would be negative. So that's how you would see that in a PFET, your VDS should be negative, right? Your VGS should be negative. While in the NFET, we saw that VGS has to be positive and VDS has to be positive. Okay. So this is the basic understanding we have about. And what about the body? You can ask, because there's another terminal which we talked about, bulk. Typically, VBS, we always, because body is tied to the source, because if you see, we are defining all these voltages with respect to a source terminal, right? It's the voltage difference which we are defining. So that means because we have to make some reference terminal based on this, which we can define the voltages. So you see the VBS typically is always made to 0, tied to source, right? So that means it does not affect the operation. And then we'll look in little more detail what happens when we change VBS later. So now the next part which we will see is about the DC characteristic after the operation.